Hi everyone, my name is Santos. I'm from Unesp, São José do Rio Preto, Brazil, and today I'm going to talk about geometry of bifurcation set of unfolding of functions with singularity A3, A4, and D4. This works together with Professor Kentaro Sage from Kobe University in Japan. We basically study the geometry properties of bifurcation sets of an unfolding when we type on unfolding. When this set, the bifurcation, is either a cuspidal edge, a swallowtail, or a singularity D4. We study case by case, right? And for example, we suppose that the bifurcation set is a cuspidal edge and study geometric invariants, and so with the others. Let's start with some definitions. Let f from Rm to R be a function. Another function, capital F, this way is called an unfolding of f. It satisfies this condition. The catastrophe set of an unfolding f is defined by this, and the bifurcation set by this set. Catastrophe set and bifurcation set are very famous in singularity theory. Another definition is of Morse family. An unfolding f is a Morse family of f if 0 is a critical point of f and this condition is satisfied. This condition is very important to prove that, together with the implicit function theorem, to prove that the catastrophe set is an r-dimensional submanifold of Rm times Rr, and more than this, in our case, we use R as 3, and we use this condition to prove that the bifurcation set will be a two-dimensional surface. It's known from singularity theory that if we take f as a A3 singularity at origin, so the bifurcation set of any Morse family of f, any unfold, which is a Morse family of f, is a cuspidal edge. So if we take any function, A3, so the bifurcation set will be a cuspidal edge. In the same way, if we take f as a A4 singularity at origin, so the bifurcation set will be a swallowtail. If we take f as a D4 minus singularity, the bifurcation set will be a pyramid, and D4 plus the bifurcation set will be a purse. There is this for surface. Definition. Let f1 and f2 be Morse families of small f1 and small f2. So they are PR plus isometry equivalent if there exists a triple, small g, big G, and small h, with this way, such that f2 is equal f1 of g bar plus small h, and g bar is small g, big G. The definition of PR plus equivalence is already known, and it is the same of this, but here we add the name isometric, and we require that G, the big G, is isometry and not only a diffeomorphism. The reason is explained in this lemma. This lemma says that if two Morse families, f1 and f2, are PR plus equivalent, as above, without the isometric, so the bifurcation set satisfies this. So the big G takes the bifurcation set of f1 into bifurcation set of f2. So in this case, if we require G as an isometry, so the bifurcation set, so if we two Morse families PR plus isometric equivalent, they have the bifurcation sets isometric. So the properties geometric are not changed, and this is the reason we require G as an isometry. Now, using the definition of PR plus isometric equivalence, we prove that any Morse family of an A3, A4, and D4 in singularity is PR plus isometric to one of these Morse families. For example, if we want to study geometric properties of a cuspidal edge, so I have to take F as a A3 singularity, so I can guarantee that bifurcation set will be a cuspidal edge, and take any Morse family, and more than this Morse family is PR plus isometry to this Morse family. So with this thought, we can suppose that our Morse family is something like that, right? The similar thought if I want to study a swallowtail, for example. So I take an A4 singularity, any Morse family, and actually I just need to study this type of Morse family because any Morse family is PR plus isometric to this Morse family, and so the bifurcation set would be isometric. And the same occurs with D4 plus minus. The Morse family I can suppose that is like that. We can get with some more conditions. For example, we can simplify even more this function g1, g2 this way and this way. Actually, these conditions came from the hypothesis of Morse family, right? These constants cannot be zero. And these conditions is actually just a simplification of G1 and G2. What is these coefficients? And the coefficient G1, 0, 1, 0, for example, is the coefficient of y in the G1. Right? The definition is here. Right? This coefficient is the coefficient of z in G1. This is coefficient of z in G2. Okay? So let's start with cuspidal edge. So we need to take an A3 singularity function, a small f, A3 singularity function. And as I said, I can suppose that the Morse family is the unfolding is like that. Has G's weight. And using the implicit function theorem, again, we can obtain a parameterization of the bifurcation set of f as this. B of EUV is X UV and Y UV and V. And moreover, we can obtain the singular set of B, and this set is the U-axis. And the vector field, we also have the unit normal vector field. And the null vector field on a circular curve, which is the U-axis, is given by partial V. That means that BV is 0 on the singular curve. With all of this information, we are able to compute some famous geometric invariants of cuspidal edge. And they are singular curvature, limited normal curvature, cuspidal curvature, and cusp direction torsion. For example, if I want to compute the cusp direction torsion, we just need of coefficient of y, z of g1 and the coefficients of x of g1. So in the case of cusp direction torsion, I just need the coefficients of g1, actually two of them, right? Another example, the cusp curvature, I only need the coefficient of y of g2 and the coefficient of x of g1, right? So just some coefficients of g1 and g2 is sufficient to give me the invariant geometry of the cuspidal edge. Next, if you wanna study the geometric invariance of a swallowtail, so first we need to take an A4 singularity function, and as I said by this slide, in this slide, I can suppose that the Morse family, the unfolding of my first function, is like that, as this way. Using the implicit function theorem again, we can obtain a parameterization of bifurcation set of f as this way, something very similar to cuspidal edge. BUV equal x UV y depending on UV and V. Moreover, the unit number vector field is very similar as well, and the singular curve is not the same in this case, but the null vector field on the singular curve is the same, which means that the derivatives of b in relation to v is 0 on the singular curve. And with all of this, again, we are able to calculate some famous geometric invariants of swallowtail. And some of them are normalized cuspidal curvature, normalized productor curvature, limited singular curvature, and limited cuspidal curvature. And for example, if I want the normalized cuspidal curvature in the point of swallowtail, right? So I only need the coefficients of y in the G2, the coefficients of x in G1, and the coefficient of z in G3. So only these three coefficients is sufficient to give me the normalized cuspidal curvature. Another example, limited singular curvature. We only need two coefficient of z in G3, the coefficients of y and G2. It is worth noting that the coefficient of each invariant in the denominator, for example, G1, 1, 0, 0, G3, 0, 0, 1, they are all of them non-zero by this condition, right? This one, actually, they are all positives. And this came from the conditions of Morse family, right? So they are all of them well defined, and this as well in the cuspidal edge. Finally, we studied the bifurcation set of unfolded of a D4 minus singularity function. We can suppose, as I said, that the Morse family, the unfolding, is like that. Now, in this case, we change the coordinate by u being r cosine 2 theta and v being r sine 2 theta. After change, this equation can be solved by r as plus or minus g3 of x. This x is x, y, and z, right? It's the three parameters, where epsilon would be the plus or minus 1. And now, if we proceed with either epsilon 1 or minus 1, we will get the parameterization of different parts of the D4 singularity surface of the pyramid, right? Let's say that if we proceed with epsilon plus 1, so we parameterize this part, and epsilon minus 1 this part, right? We note that the way you change the coordinates implies that parameterization of B covers the surface twice. The reason is this 2 theta, right? We need to do this 2 theta in not only 1 theta, because the unit vector field, normal vector field, right? That's not possible if we not do this. So, but doing this, so B covers the surface twice, and we need to be careful with this. By the implicit function theorem, we can obtain a local parameterization of the bifurcation set as, again, the same way, but we need to be more careful. The singular set of B is given in the following figure. For example, for one of this side of the parameter, this side, for example, when epsilon is 1, the singular set is these curves, right? Why did I put this only half of the circle? The reason is this. Since B curves covers the surface twice, so I won't need to study this part, because the other part is the same thing, right? And for epsilon minus 1, I can study only this half of circle, and the singular set is this curves in black, right? Moreover, I separated the face of parameter. Of course, the parameter has in each side 3 regular parts and 3 singular curves, and I called phase 1, phase 2, and phase 3, right? And on the other side, phase 1, phase 2, and phase 3. If we take the most simple parameter, this one, for example, so the phase 1 is in front of the phase 1, phase 2 in front of the phase 2, and the phase 3 as well. And defined x and y, this equation, this function, okay? So the unit number vector field can be taken as ni equal ni1 above the norm of ni1, where ni1 is this. So we can get the unit number vector field once we made this change of coordinate, right? And more than this, if we consider the Gaussian and the mean curvature of the bifurcation set in the neighborhood of the origin of parameter singularity, in neighborhood of the origin, or in one neighborhood of the origin, this is the origin, right? So we can get that Gaussian curvature is something like that, and the mean curvature is something like that. Lambda, in this case, is for epsilon 1, okay? So in this case, when lambda is 1, so lambda in this case is sine of 3 theta. For epsilon minus 1, it is cosine 3 theta. And this is the identifier of singular curves, right? So the Gaussian curvature is unbounded near the origin because of this z square, and so the mean curvature is because of this z square. We can also compute the principal curvatures, kappa 1 and kappa 2, for example. Kappa 1 in this case is the maximum curvature, and kappa 2 the minimum curvature. And with this calculate, we conclude that one of these principal curvature is bounded near the region, actually the minimum one, while the other one is unbounded. Now we consider the number of ridge curves, subparabolic curves, and parabolic curves in the pyramid. For example, there are at most 5 ridge curves relative to principal curvature kappa 1 and 11 relative to kappa 2, passing through the region of bifurcation set of an unfolding of D for singularity. So if we take D for singularity, so the bifurcation set will be this singularity, D for singularity, in this case a pyramid. And if you consider the number of parabolic curve passing through the region, right, this way, for example, if the parabolic curve pass this way, so we say that it is in the phase 1, phase 2, and phase 3. Okay, so the number of ridge is 5, the ridge relative to maximum curvature, and relative to minimum curvature we have 11, at most 11, right? There is no exactly 11, but at most. And if you consider the subparabolic curves relative to minimum curvature, there is no curvature, and relative to maximum, and there is 5 subparabolic curves relative to kappa 2. Actually, at most 5, right? And if we consider the parabolic curves, the number of parabolic curves passing through the origin here, for example, the maximum number is 3. So we have at most 3 parabolic curves passing through the region. In this part of the fourth singularity of pyramid, and this part as well, we have at most 3 there and 3 here. Okay, and one result very interesting is the case on where there is exactly 1 parabolic in each phase is impossible. That's not happen. And we summarize all of this in this table. Let's explain this table. The number of parabolic curves in each phase can be found just looking at the coefficients of G1, 0, 0, 3, the coefficients of Z in G1, the coefficients of Z squared in G2, and the coefficients of Z of G3. Z squared of G1, Z squared of G2, and Z of the G3. And more specifically, we only need to check the sign to see the sign of the 5 following constants. These constants, these 2 constants, where is plus and minus, and these 2 constants. So we have 5 constants. We need to check the sign of these functions and this constant. And with the sign of this constant, for example, if all of them is plus, all of this 5 constant is positive, so we have 1 parabolic curves in the phase 3 and 2 in the phase 2. And in the case there is only 1 parabolic curve, it will be in the phase 3. There is no way to exist 2 parabolic curves. Either there exists 3 curves or only 1 parabolic curves. And this table is our final results, my bibliography, and thank you very much.